A basic statistical primer review thing for you this week. We're in week 3, but this could really pertain to week 4, 5, 6 as well. Uh, John Tukey is a famous statistician, and he invented all kinds of well-known by statistics experts algorithms and mathematical formulas. He invented some simpler things too that we're all familiar with, like the box plot. And I guess he's given credit for coining the term bit, as in bits and bytes. So he had this quote basically that statistics is a science, not a branch of mathematics, but uses mathematical models as essential tools. Statistics is, for lack of a better way of describing it, and this is my vernacular, gives us a way of looking at things, a way of examining things, a way of making sense of data when you get right down to it. There are descriptive statistics and there are inferential statistics. Descriptive statistics are the kind of things you might normally consider, things like census information, population facts, facts about any given entity, usually numerical summaries of things. They use both numerical and graphical methods to represent these things. Inferential statistics, which is something we're going to be interested in, is using or looking at statistics as a way to make predictions or a way to interpret populations and data. So it involves generalizing from a population, estimating things about a population, testing hypotheses. Obviously, we know inferential statistics from political polling and predictions that are made every time election year rolls around. So those types of statistics are more in the inferential area. So the population is the entire collection of people or objects or things, they don't always have to be people, about which information is desired. And like I say, well, they don't always have to be people. In scientific statistics, we could be studying plant forms or insect breeds, that sort of thing. But in marketing and marketing communications and business statistics, we are usually, as you can imagine, generally looking at human beings. So a population, though, is not the entire, say, 320 million American citizens. It would be a population of basketball users. A sample would be a subset of that population selected in some prescribed manner for study. So if we're going to study how many basketball purchases are made by athletes over the course of a lifetime, we would have to basically get determination about people's athletic ability, their interest in sports, and kind of label them as an athlete or as a non-athlete. And then we would have to examine their interest in basketball, things like how many basketballs do they buy? Do they have a professional interest in it or a recreational interest in it? Or are they just parents buying for their children? This might be something that would benefit a manufacturer or a sporting goods provider, those sorts of things. Statisticians, as most of you guys know from your work or previous courses, are concerned with a couple of things. They're concerned with the numbers, the raw numbers, where they lie, things like means and averages. Average and mean are obviously the same thing in almost all cases, but I generally define means as more specific to the population being studied. The median is the middle point in the data. We're going to talk more about these in a second. And they're also concerned about variability, variances within the data that suggest different ranges and different users, different tendencies among the observations, that sort of thing. I guess the core number that always comes up in any statistical analysis, no matter whether you're doing it by hand, which we won't do, don't worry. No remembering statistical notation or numbers with hats and X's with dashes and that sort of thing. We will use computers for that. To find the mean in any set of observations, as it says here, you add their values and divide by the number of observations. That's all laid out here. And observations, as shown by the statistical notation on their left, becomes the mean, shown in that next little diagram down toward the bottom. And even in a more kind of awesome notation, x hat equals that sigma sign and all that stuff over on the bottom right. As I say, we're going to use the tools we have, Excel or Sheets, and we're going to use R for all that. But it's still pretty simply the average. So an example here is 8 different book lengths, all laid out. You see each book length. Name your book, call it X1, name book 2, X2. He's got 312 pages, and so on. You basically add them up, you get a total, you divide by whatever number there are here. I think it's 8, obviously, and you've got your mean. Median is a little different. It's the midpoint, right? So the number of, you would take all the observations, add them up, and you would take the middle number. Now, a lot of times a set of data, even fairly large sets, might not have an exact middle because it might have an even number of observations. In that case, you take the 2 center observations and you take the mean of those 2 center observations to determine your median for the entire data set. It's kind of a complicated sounding way of doing a fairly simple thing. All data, though, is laid out in kind of on a plane or even on a vertical plane where you show all the observations and they go from the minimum to the maximum generally. We've all seen the bell curves, those sorts of things. But you arrange the observations in a kind of a traditional way, left to right. You locate the median. The first quartile and the third quartile are important because those are basically the medians that first appear. We divide basically the data into 4 quarters. The first one would be those items where everything to the left would be closer to the minimum and everything to the right of the third quartile would be closer to the maximum. Or we can look at it vertically, as we will do here in a second. Here we see a group of observations where the minimum, as you see down at the base, is 0. The maximum is 2.4, 2.5, something like that. The median observation, though, is a little under 1, or it's about 0.7, it looks like there. And the interquartile range, where half the data is between like 1.2 at the top end and 0.44 or 0.45 at the bottom end. So half of all those observations are right there in that, it's abbreviated as IQR or interquartile range. On another illustration, it might look like the big point of the bell is right there. So that is another way of looking at it. A lot of box plots or box and whisker plots that you look at are set up vertically. That's why I show you this too. So back to our book pages length in the whole median example. You order the list. Here you've got the whole range, and there are 2 middle numbers, 258 and 286. the median is the average of these two numbers, which is 272. Now, there's also another M word that's sometimes used in association with statistics, and we're not going to talk much about that, but that's mode. That's where most of the observations are. That is a data point that is most frequently observed. That can be meaningful, or it can be very unmeaningful. So it all depends. Oftentimes you might find a mode point near the median or the mean in data. Typically, all statistical programs in one form or another, and as I say, I'm sure you guys have had statistics classes, and that's not the point of this. It's just kind of a review. I need to do it myself, actually. The minimum quartile 1, medium Q3, which is quartile 3, and maximum are key numbers that are always observed and frequently given in any statistical printout of relating to data. And it's usually done for more than, when you're comparing tendencies, you get more than one. And we'll see that when we use R. Here's a basic box plot. These are earnings looking at only kind of two variables, sex and race, and they show differences, obviously, in earnings depending on race and sex. And I have to say this looks like it's old data just based on the salary ranges, but it gives you an example. Okay, the 5-number survey is a fairly common way of looking at a data set. Another way is to take a look at the sample variance and the standard deviation. A sample variance is something that is kind of a mystery to intro statistics students. Any student really is. What the heck do we have it for? It's a set of observations, as this slide says, averaging the squares of deviations of the observations from their mean. Simply put, if you had a theoretical set of data and it was a real small set, say it's 5 observations, all women, 38, 40, 43, 46, and 49, you would have a mean in that. So you would average that and you would get that particular mean. What you would come up with was the number 43.2. So to get the difference from the mean from each of the 5 observations, you would subtract 43.2 from 46 and 49, and also subtract 38, 40, and 43 from 43.2. In the case of 43, the difference is only 0.2. In the case of 40, the difference is what, 2.8, something like that. Actually, it's 3.2. So you take all of those differences, square them, add them up, and you come up with what looks to be a ridiculously high number of 78.76. And then you divide that by 4, which is n. Your n is 5 in this case, minus 1. And you get a variance of 19.69. Again, a relatively meaningless number, until you take the square root of that, which equals, in my case, 4.43. You can do the math yourself. Let me know if you come up with something different. So the 4.43 kind of is a representation of how far from the mean the average observations are. Imagine now substituting the data point, the 38-year-old woman, and putting in a 19-year-old, and then taking the 46 and replacing that with 98. You'd have a much wider range, much greater difference, and ultimately your standard deviation would be much higher. You can try that one at home though, and if you want send it to me and I'll let you know what I came up with. Again, standard deviation is the square root of the variance, which, as I just said, is relatively meaningless for anything other than getting the standard deviation. It's important to kind of take note of the fact and observe generally that all this adding and subtracting to get variances and ultimately a standard deviation is relatively tedious by hand. That's why we have computers, though, isn't it? Basically, it's viewed that the 5-number summary is better than using the mean and standard deviation for describing distribution or distributions with extreme outliers. The standard deviation, variance and standard deviation, is considered to be good, though, for reasonably symmetric distributions that are free of outliers. Probably a good idea in a lot of cases, however, to take a look at both, at least initially. Now let's take a look at inference. Inference is just what it sounds like. Basically, we infer things. We try to draw conclusions from looking at the data. Conclusions take into account the natural variability, and inference relies somewhat on probability to describe a chance variation. There are two common types of statistical inference. These are the most common and the ones I personally am most familiar with, and most people that work with statistics are. The first one is the idea of the confidence interval for estimating the value of a population parameter. Second one is a test of significance, which assesses the evidence for the claim being made. Both are based on sampling distribution. Parameters in statistics. These are important too. A parameter is the number that describes the population. It's a fixed number that we don't truly know the value of yet. A statistic is a number that describes a sample. The value of a statistic is known when we have taken a sample, but it can change from sample to sample. You hear terms like t-value, p-value, even the mean is a statistics, or the mode. Those are all statistics. Okay, that should do it for this short statistics kind of primer. This is actually part one of a two-part series. The second one I will put up next week for you. It is kind of a refresher for those of you guys familiar with statistical concepts, and I guess an introduction for those of you who aren't. I encourage everyone to look at the online statistical textbook at the top of the Moodle page. This thing is actually very handy. It gives you quick definitions of things, tells you how to make or assume how basic calculations are made. One of the reasons we use computers is just to eliminate a lot of the drudgery, which you've sort of been introduced to, at least as an idea, in this video. The computer can do all these time-consuming calculations much faster than humans can. It's hard to imagine that there was even a field of statistics prior to the advent of the computer. Best thing to do with this is probably just look under what are basic statistics and go down and look at, take those bullet points point by point until you get tired. Then you can always use this as a resource for future use. You'll probably use this more as a reference tool than as a reading. So go with that. You can also look at some of those things on the left if you want to get a basic primer, elementary concepts, basic statistics. We're not going to get too much into things like ANOVA or conical, or we may do some regression stuff with our exercise at the end of the course. Anyway, that's it for this one.